Okay, if people want to be admitted, I'll admit them. Okay, what's up, guys? How's everything going? You ready for some more math? Yeah, okay. Zoom people, can you hear me?
Yes.
Yes.
Okay, there's a weird sound coming from my laptop. I don't know what's going on. Hopefully nothing will happen. Okay, so today I'm showing the board. Remember this board? We're gonna continue with 2 more twists on the linear regression, and then we're gonna be talking about how we find the optimal parameters, which is where we said we're gonna do today, using a method called gradient descent. Okay, so hopefully you've heard of this name. I just want to add to this board to pick up from last week. I want to add the formula for the minimum mean squared error. So we remember. Is there's looking? Oh, okay. So we remember that the mean squared error is the average distance between the point and the prediction that we give it of the line. That's the error. We take that distance and we square it, and then we do an average. So the formula, the way I'm writing it, I'll do it in red. You guys can help me if you remember. It's the sum. Okay, so instead of writing the sigma, the sigma sign, I'm just writing sum of our prediction, which is the y predicted, minus the actual real y squared to the power of 2, right? Because it's the error squared. And because we want the mean and not the sum, we take this whole thing and we divide it by n, right? Yeah. N is the length of the number of samples we have or whatever. Okay, so this is the mean squared error. All right. And I'm also going to add the formulas for the regularization factors. Remember, the regularization factors is the modified loss function. So we can take the mean squared error loss function, for example. But we add to it a regularization factor. So the L2, let's keep doing it. Want to find the minimum of the MSC. We know the mean squared error, plus the sum of all the parameters squared. So I'm doing a big B to mean all B0, B1, B2, B3, all of the B's. I'm writing them in big B. It could be that you see it with the theta in other places, right? Theta 0, theta 1. I think in regressions, people from statistics use B and people from machine learning use theta, but I'm used to the B's, okay? All right, so we want to find not only the minimum MSC, but we want to find the minimum MSC and the sum of the betas. And for the L1 regression, we want to find the minimum MSC and the absolute value of the betas, the sum of the absolute values. Yeah, everything okay? Yeah, more people.
I had a question about the L1 and L2.
Yes.
In relation to the MSE and the MAE. Absolute.
Yes.
Is there a preference for using like L1 with the absolute error and L2 with the squared error?
So I've heard that. People use the L1 more when they use the mean absolute error and the L2 with the mean squared error. I don't know why. So I don't have an answer.
Like absolute.
Right. That's it. It looks like nicely, right? But it doesn't really change. The reason people use the mean squared error is because we'll get to it in our third twist, but because it usually finds the average the line, which is the average line. And the mean absolute error is the line which is the median line. So it has nothing to do with the regularization. It's just do we want a line that goes through the average of the points, or do I want a line that goes through the median of the points? So that's the reason for using MSE or MAE. And then the regularization, as we said, we either shrink a little bit our parameters because we say, oh, they're too extreme, we want to shrink them, or we want to push some of the parameters to 0 because we say, oh, we have too many parameters, we want to sparse them. But yeah, people do it. I don't know. Maybe there's a reason that I'm missing. Okay. Yeah, in both of these cases, I did MSE plus the regularization factor. By the way, we can invent a new loss function and then add the regularization factor to that new loss function. We're allowed to do that, okay? It's not just that it's easy to use loss functions, which already have like the Python code for them, okay? All right, another thing that I wanted to talk about last week, and I forgot, is remember when we said we can transform the data? Let's do this in purple. It's going to be a colorful lecture. There is one transformation of the data that is very common and good to use, and it's called normalizing the data or z-scoring the data. So instead of using the values of the data, we normalize or convert them into z-score by going for each value of the data x, we do minus x, the mean, which is x hat. I don't know how to do hat besides this way. Divided by the standard deviation. Okay, so instead of using the absolute, I'm writing Sx, the standard deviation. So instead of using the actual values that we measured, let's say the actual hippocampus size, we do the hippocampus size minus the average hippocampus size divided by standard deviation, which essentially gives you the value in standard deviations away from the mean. So how many standard deviations you are away from the mean. And why is this good? Because it helps all the different x's that we have the same units. Usually it's around 0, right? Because things that are close to the average will get close to 0. And even things which are extreme will get somewhere between -5 and 5. Excuse me, because it's very rare to find data points that are more than 5 standard deviations away from the average. And then it helps the computer approximate and stuff. And so it kind of standardizes the units. And that's very good practice. So normalizing or z-scoring, okay, it's the same thing. Excellent. So we're ready for our third twist. Yeah, are we ready? Yes. Yes, I don't know what's going on. It's the first time it's been doing it, and well, hopefully it will quiet down. I opened Task Manager to see if there's anything weird here, but it's only the Zoom that's
Sometimes it makes
yeah?
it go weird.
If you think I should unplug it?
No, sometimes like not even like it doesn't mean you have to change it in BIOS, like from AC to DC or DC to AC.
Oh, I don't know how to do that. Okay.
So it might not be fixable.
Yeah, so I'm gonna take it to the shops whenever the shop's open.
Another question.
Yes.
So what's the point of the z-score?
Of the z-score of normalizing. So let's say one of the measures you have is let's say you measure height in centimeters. So it'll be like 180, 190. And then another measure you have, I don't know, you measure something that's very small, like percent or something, and it'll be 0.1, 0.2. So the computer for the numbers, it sees big numbers and small numbers, and it can make it more difficult for it to approximate the optimal parameters. But when we normalize each one of our features, so all of our features will be somewhere between -5 and 5, right? Usually. And so the computer can approximate it faster. So it's like giving us easier numbers to work with. That's what it is. Of course, you don't have to. It's just a good practice.
And that's for when you're trying to optimize the channel or compare.
Just whenever you build a model, so instead of using the actual data, we said we can transform the data as much as we want. So one of the very common transformation is to convert them into z-scores. That's it. Okay. Excellent. Okay. So the third twist is that we can assume that the outcome, that y, comes from a probability distribution. Okay, and once we assume that y comes from some sort of probability distribution, we can assume which one. Then we can talk about the likelihood. So we can try to find parameters for that probability distribution, and we can talk about the likelihood of the data of the actual observed y that we have given those parameters. So I'm going to do a quick example, which hopefully should be very intuitive. I have a coin which is not fair. Okay, so not a fair coin. Okay. Not a fair coin, but I don't know how unfair it is. Okay, and so I toss the coin 10 times and I get 7 out of 10 heads. Okay, 7 out of 10 heads. So what I do, yeah. So I can ask, so I can say, oh, let's say that the outcome, we know it is distributed binomially, which is the distribution for repeated outcomes. And we know that the binomial distribution takes the parameter how many times we flipped it. We know we flipped it 10 times. And the p, right? That's a parameter of the distribution. And now we have to find a certain p, a certain parameter, right? Such that the probability of observing the actual y that we observed, right? So observing 7 out of 10 heads, given that p is highest, right? And this is the maximum likelihood estimation for p, because the probability of seeing the data that we saw is the likelihood of the data, and we want the maximum likelihood, right? So we can try p equals 0.2, p equals 0.3, right? We can try all kinds of numbers, or we can do different ways to find the optimal one, and we'll find the optimal p, which will give us the highest likelihood, okay? And that's our best estimation for p, okay? Now, this should be very familiar because it's very similar to what we did here in the machine learning. We picked a model, remember we picked the model type, decide on a loss function, and then we try to find the optimal parameters. So here we're using a little bit of probability. So we pick a probability distribution, and then we know each probability distribution comes with its own parameters. So the loss function that we have is the maximum likelihood. It's not a loss function, it's like a win function because you want the maximum, not the minimum. But what people sometimes do is they do negative likelihood, and then your loss is the minimum negative likelihood. And then we find the optimal parameters. So this is just a probabilistic extension to what we've been doing so far. And we get a whole new family of loss functions, which are the max likelihood estimations, right? But for that, we need to assume a probability distribution first, okay? It's not complicated. I'm using a lot of words, but it's a very simple idea in my opinion, okay? Excellent. And now, one of the things that we have to remember is that if for linear regression, if we use a linear regression and assume that the errors are normally distributed, okay? So I'm gonna show it before I'm telling you what happens, I'm gonna show it I'm gonna visualize it. So what that means is that we're assuming that for every x, let's say the hippocampus size, so our prediction will be the average of the normal distribution. Remember, normal distribution has a mean and a standard deviation. So we will predict the parameter mean, and then the actual observations. No. I wanted the scribbly one. The actual observation will come from a normal distribution around our line. So this is a sideways normal distribution, right? And then things here are kind of likely to happen and things here are kind of less likely. And for every point in our line, we have a normal distribution with the average being our line value at that point, right? But why don't all the points come from that exact value? Why is there some difference? Because it's a random variable that comes from the normal distribution. Okay, and we could have picked a different distribution, right? We could have said, oh, it comes from a very right tail distribution that looks like that, right? We could have done it, but let's say we pick a normal distribution that the errors are normally distributed around our line. So then what happens? The line or the parameters, which will give us the maximum likelihood estimate. So the MLE parameters are the same parameters that give us the minimum MSE parameters. Okay, and there's a great proof for it that we're not going to go through. I heard you guys went through it in class. If we want to go through it, we could go through it at the end of the class. Okay, and then I'll also put it on the drive. Okay, the proof. Oh no. Okay, so once again, if I'm saying I'm just going to fit a linear regression and optimize for minimum mean squared error, and Austin is saying I'm actually going to assume the errors come from a normal distribution, and then I'm going to find the line which is the maximum likelihood estimator for the mean, we're both going to find the same. Okay, excellent. And we need to remember that. Okay, we got twist number 3. Any questions about this?
Can they have the accent that they will lie? So basically, you cannot fit relationships that are not linear. Like,
Yeah, so relationships that are not linear will be twist number 4.
But you still need normally distributed values.
No, sometimes you don't have to. You can pick whatever you want. You can pick any distribution you want. You just know that once you pick the distribution, you'll have to find the parameters for that distribution, which will give you the maximum likelihood.
Oh, okay, so for other distributions, you need normally distributed values as an assumption.
No, you can assume that the errors come from any distribution that you want, but then you will have to find the parameters which maximize your likelihood given that distribution. So it gives you the highest probability of observing the Y given your parameters. Okay. All right. So I'm moving on. I just want to make sure I didn't miss anything. No, I will say I have a page of the proof that the MLE parameter for the normal distribution will minimize the mean squared error, and I'll put it on the drive, and then we can go through it on our own time. Okay, excellent. Okay, the 4th twist I think is the coolest twist. But you guys can say what you guys think. Is this? Sometimes we don't want to predict a Y which is continuous, or that the relationship between Y and all of the X's, not just a particular X, is not linear. Okay, so we said if the relationship between Y and X1, right, one of our features is not linear, just transform X1 and fit the linear regression. But sometimes the relationship between Y and all of our X's is not linear. So, right, I'm doing a B0 plus B1 times X1 plus all the way to Bn times Xn. Right, so what do? This was the linear regression, right? And we're going to do this as our prediction. So we do this crazy trick. You guys are not going to believe this. We're going to take our, what we did from the estimation, what we did, the linear estimation, and we're going to put it inside a function which is nonlinear. Okay. So, and now what we did is we generalized this idea of regression to fit any type of curve or any type of transformation that we want, or any type of Y that we want. Y doesn't even have to be continuous anymore. It depends what F you choose, right? So one F that we could choose is, let's say, the cosine function. We can choose cosine function, and then it will map from weights times the features, right, to the cosine values, right, somewhere between 0 and 2 pi. We could do that if it's interesting to us. Or we can do F will be e to the power of, or whatever, right? And this thing is called why is my mouse going crazy? Generalized linear regressions. Which, are they linear? No, they're not linear. Okay, specifically they're not, like they're definitely not linear. right? And then the guy who invented the name generalized linear regression said later that he regrets calling him that because it is confusing, because it sounds like they're linear, but they're not linear, okay?
Is there a difference between this and the transformation? Is it like a more generalized?
Yeah, so the transformations are for each individual x. That's what I was talking about. Here we're transforming the whole product between the whole like regression. Essentially, it's actually equivalent to transforming the y. And if you see, it's equivalent to doing the f minus 1, like the inverse f of y for the b times x, right? Because you can do if the function has an inverse function, so you can inverse the y instead of the, right? So you guys know about inverse functions? Yeah. So let's say the f was e to the power of, so the inverse is the logarithm. So the log of y can be the b's times the x's, or the y can be e to the power of, right? So that's what it is. That's what it is. And then this function, the inverse function is called the link function. But usually we talk about not the link function, but the inverse of the link. Okay, I'm gonna write this small. Yes.
Yes, so, I have this question. Basically, imagine you have some data and you try to fit linear regression.
Yes.
And you notice that there isn't a linear relation, but the errors are normally distributed.
Yes.
Would you go for a linear regression or for a generalized model?
So you can go for a generalized model and assume the errors are normally distributed. You can go for that one. It's okay. And then you have to make sure that you fit with the parameter that you maximize using the normal distribution probability, right? But then the line that you fit can have that one. In that specific case, if your y is continuous, it has to be continuous if the errors are normally distributed, because normally distributed errors will give you continuous numbers, right? Okay. So I would still go with a linear regression, but I might try a polynomial regression, which we said it's not exactly linear.
Instead of a generalized.
Yes, generalized. Now we're going to see, I'm going to give 5 examples of good generalized linear regressions to know, and we'll see in which cases they're good, okay? But we can invent any number of more generalized. Yes. So remember that the generalized linear regression is y is some f of what we did up till now. So the link function is the name of the inverse of that f. So we can also say f of y is a linear regression, is a like b0 plus b1 times x1. So this is called the link function. But usually we talk about this function, the inverse of the link function, okay? All right, so now look what I prepared for you guys. You guys are not going to believe this. An amazing photo illustration. Where are we going to put it on the board? Of course, it's not going to work. Woohoo! Where are we going to put it? Here is good, or here? Let's put it here. Let's extend the board this way and put it here. Amazing illustration. It's gonna be in the drive as well, of 5 types of generalized linear regression, and we're gonna talk a little bit about each one. Cool, huh? Woohoo! Okay. Excellent. So the first one is the regular linear regression, except with the errors are normally distributed. So it's a maximum likelihood. We want to predict a value given x, and this is a big X, which means it can have a lot of features, not just one feature. All of them can have a lot of features. And it's good for continuous values. So for example, it's good for brain size. We want to predict the brain size given some x. And this is how the function looks. And the link function is the identity. Identity just means 1 times that. So it does nothing. Oh, and I forgot to say, this is the notation we're going to be using from now on for, instead of writing b0 times 1 plus b1 times x1 plus b2 times x2. Remember that we wrote, yeah? I'm going to go through this because this is important. remember that we wrote this whole thing tediously, b0 plus b1 times x1 plus b2 times x2 all the way to bn. So instead of that, we're going to be writing here they chose beta, beta transform times x, which is a different way to say that this is the dot product between the beta vector, which is the vector of all the weights, and the x, which are all the values in our data point, all the features. Okay, is this clear to everyone? This jump? Okay, excellent. All right, so, and we know that mu, the mean of the normal distribution for the errors, is just equal to linear regression, the red line, and then the actual y comes from a normally distributed around that line. Okay, so here instead of a number mu, it's a number for every x or combination of x's. Okay, cool. Next one that we should know, this is a good one. It's called the Poisson or the log linear regression. This one is good when you want to predict occurrences given x. Occurrences means count data, or more specifically, count per time or count per unit. So let's say you want to predict how many times the bus comes to the station per hour, right? So you can't have negative because you can't have negative counts, but you can have 0, 1, 2, 3. Oh, and they have to be integers. You can't have 1.5. You can have that that on average it comes 1.5 times per hour, but your data that you see are counts, so they have to be integers. Okay. And then the classic example is spikes per second, right? We all know that the neuron fires in spikes per second, and then we can count how many spikes there were. The distribution looks like this. The link function is the logarithm, but usually what we do, the Poisson function, the Poisson distribution has one parameter, which is, it's called the lambda parameter or the rate parameter. And the rate parameter is simply e to the power of our linear regression, okay? Poisson is very, very good for count data. If you fit a linear model on count data, it's not so good because it will give you negative values and stuff like that, which is impossible for count data. Yes.
So e to the power of the transpose.
Yeah, b0. That's your lambda because the Poisson has lambda, not p. And yeah, that's what it is. So for, let's say you do, so let's say for small values of x, you'll get a small rate. And then for large values of x, you'll get a large rate. And you will see more counts. And the larger values, and when I say x, I mean, I'm sorry, I should say x multiplied by our weights, because we want to find the optimal weights, right? So it could be that the large value of x will actually be multiplied by negative weights, and then we'll get a negative value and so on, okay? Yes?
So the y, the dependent variable has to be discrete, but the x variables can be anything.
Right, so for all of them, the x variables can be anything. The dependent variable is discrete, is counts. But the rate parameter, which is actually what's more interesting for us, because that's what we're trying to estimate in the red line, doesn't even have to be discrete. The lambda parameter, the rate parameter, doesn't have, because something can happen 1.5 times per hour, but we're never going to observe 1.5. We're going to observe 1, 2, 3, right? Okay, but this is what is interesting for us in the Poisson regression. Cool? All right, this is going quickly. I'm glad. Logistic regression. It's very, very cool. And actually, you predict a probability given an x. So probability means that you can predict a number between 0 and 1, but can never predict negative numbers or higher than 1, right? Because that's not probability. It's very good for binary data. For example, a forced choice test. So in psychology, a lot of times, or actually also with rats or whatever, they have two choices. You have to click right or left or something like that. So if you want to predict the probability of clicking right or the probability the rat will turn right, logistic regression is very, very good for you. But the logistic regression, the link function is the logit, but the actual thing is that we use a Bernoulli, which is like the binomial. Bernoulli is the binomial with one event. And the P is 1 over 1 plus E minus our regression. Okay, so it's a little bit of a confusing function here, f, but that's what it is. And then it fits a red line, which is always bounded between 0 and 1, so it's a probability. And then you can see at like low values of x, for example, or low value, it will give a low probability of something happening. And for high values, it will give a high probability of something happening. And in the middle, it will give like a middle probability. And you see here, the y-axis, the points aren't very clear, but they're either 0, it didn't happen, or 1, it did happen. Okay, excellent. So that's a logistic regression. Yes.
So we have also provided regression classification tasks.
Yes.
So today we covered inside for the classification task, logistic and the perceptron.
Yes.
But all of them are just linear regressions.
So they're generalized linear
Yeah.
regression. Yes.
Okay, but why we then consider courses two for classification?
Okay, good question. So I'm going to say what I didn't say is that logistic regression, as I described it, is not classification because it gives you a probability. So probability is not a classification. But what you couldn't do is you use that probability to predict the class, either happened or not happened, 0 or 1. So once you use that probability to say happened or not happened, you're doing a classifying. You're saying it either y is either happening 0 or 1, happened or didn't happen. So that's why the logistic regression is used for binary classification. Okay, but the root of the logistic regression is to give you a probability. And then usually what we say is if it's higher than 0.5, it happened, we'll predict that's going to happen. If it's less than 0.5, we're going to predict it's not going to happen. Okay. So because you mentioned the sign, the perceptron, sign regression, we're going to say the same thing. Sign regression is the same thing. It also predicts a binary class given x. And the link function is the sign. So what you do is you do your weights multiplied by features, right? And then you see if it's larger or greater than 0, you give 1, say it's positive. And if it's negative, you say it's negative. And then you classify that to a class, either the negative class or the positive class. And the way it looks is like this, a step. And at 0, it moves from negative to positive. Okay, so for a good example to use this is on health status. You multiply all the weights by all the features, and then you see if it's positive, the person's healthy. If it's negative, the person is has a certain okay. So that's why they're classification, because the y, the outcome, is binary. It's discrete. It's 2 options. Okay.
Okay, so we have this whole generalized regression, but we use each of them for different tasks. For example, we use linear regression to predict the value.
Yes.
Both of them for
Exactly. You can also say that classifying is predicting a discrete non-ordered value. So it's all for prediction. It depends what we want to predict. Yes, there was a question in the back.
So the sign is for binary class, but then logistic is also for probability, but is it more than just binary class? Because I thought it was the same for binary class for sign.
So they're both binary. You see, this is also binary. The logistic regression gives you the probability, and the sign doesn't talk about probabilities at all. As you can see, the reason the sign and the ordinal are not in blue is because they don't have the probability distribution. So we're not talking about likelihood with them. We can't. There is no probability. Okay. So that it's a different way. Yes.
There's someone in the waiting room.
Oh, good call. Okay, so we're going to be talking about the perceptron a lot more next week. Okay, so this is just a thing. Ooh, wow. Yes.
Do we send threshold probabilities to what's one and what's one, or do we get that from the?
You decide the threshold, but it's almost always you say half. Because if you have a different threshold, it will be incorporated into your regression in the B0 term. So it's a little bit of math there, but your B0 term in the regression, which is the first coefficient, right? It's the intercept, it's the first way, kind of adjusts for the baseline probability, and then the rest of the features and the rest of the betas will adjust for the movement depending on the features. So we'll say if the features increase the probability or decrease. But that's a specific thing which happens with logistic regression. It's a very specific thing. But of course, you can do whatever you want. Usually, what you do is you do 2 lines of code. The first line of code is like logistic regression give me like the prediction, and then it gives you a number between 0 and 1. And then the second line of code is you're like, if bigger than half, predict class 1. If less than half, predict class 0. Okay, you understood? Okay, and then the ordinal, I'm going to mention it because just so you know about it, but it's really not that important. Sometimes you predict an ordered class, which is not continuous. So a good example is a happiness questionnaire when people say I'm like sad, neutral, happy, or something like that. So there is an order there, but they're discrete units. It's not a continuous value. It's not like 0, 1, right? So there's a trick. It's called the ordinal regression, where you actually use the logistic function, but then you fit k more parameters, which are the cutoff points, and then you get a certain p from the logistic function, which, as we said, returns a p between 0 and 1. And then you see where it falls between the cutoff k points, and that's where you predict it to a class. So if it falls here, you would say this is like very unhappy, unhappy, neutral, happy, happy, very happy. Okay, but I don't want to go into it further. Yes.
I just have a quick question about this. Like, if you have this happiness questionnaire, but instead of having 3 categories, for example, you have a discrete score with
Yes.
levels, like 60 points from 0 to 60. Do you think it's more appropriate to use a Poisson or an ordinal?
So ordinal is good when you have like 5, 10 classes, because you have to fit the parameters k for every class, because you have to find the cutoff point. So if you have 60 points, you're going to have to find 60 more parameters. That's a lot.
Even if there is an order to them, then
yeah.
Poisson.
But if there's an order to them and there's 60 points, I don't know, I might even do a linear regression and just predict the line. And it's between 0 and 60. I know it's count data, but it could be.
When you say count data, then you mean like less a smaller range of the value.
No, I mean count data is counts per time. So it's per unit time how many things are likely to happen. So that's a Poisson. So you could say per questionnaire how many counts of scores I'm gonna get. I don't know if it's like interesting to find it could be. I don't know. You have to also look at the data and see which one fits better and stuff like that. That's also okay to do. Yeah. All right, we good with the GLMs? Yes.
It's not clear to me why you would use a generalized for linear regression when the errors for I don't know.
What a different one than the linear one.
Yeah, I think that was a question.
Yeah, so let's say your y. Okay, so we agree that if the points do not fall on a linear line, right? Okay, so let's draw this out. Let's say this is a case. It's true that you wouldn't use any one of these particular 5 generalized linear regressions if their errors are normally distributed. But it could be a case that you have 2 classes. It's a signal detection theory. So you have a class. How am I going to do this? Oh, I know how am I going to do this. You have let's say you have false 2 classes. So 2, and then you. Okay, let's say you have reading scores, reading times from people who are either kids who are either healthy or have dyslexia. So the kids who are healthy, the kids who are healthy, and I'm doing the histogram of the reading scores. So this is their reading time, and the kids who have dyslexia, this is their reading time. So these are 2 normal distributions, but we know that the kids with dyslexia are on average longer, okay? But if you look at the specific error from the average, so for the kids with the healthy kids and the kids with dyslexia, the errors are normally distributed. It's just around 2 different averages, okay? So we know we only are looking for 2 different averages, so not a whole range of continuous averages, and we know that the errors are normally distributed around each one. So we can fit a GLM for that, which will predict me like two numbers, two values, two averages. Now, in this particular case, a linear function would also work. The linear function will just find the average of this group and the average of this group. But I can imagine more complicated cases where linear functions won't work and the errors are still normally distributed. Okay? No problem. It's good questions. And it's also, I'm glad that you guys are asking questions, it means you're listening. Yeah, no, go for it. We good with the, so the way I see it, we finished this board, which is my, oh, we want to go into how we find, but this is the linear, the regressions board. Yes.
Why do we
Because it's like a specific part of it, and this is the specific time when we assume that they're normally distributed. So I kind of put it in. It's yeah, it's like a specific. That's how they classify it. It's like the non-generalized linear regression is just linear, but yeah.
So like generalized regressions are the family?
Yes. Yeah, generalized linear regression are all the family, and it's all the regressions where the form is our prediction y is some f of our features times weights, okay? And then we know particular ones which are good, which are useful if you can assume the probability distributions or you know something about the shape of the data. These particular ones are useful, but there are more. There are loads others, okay? Cool. Okay, I'm gonna move on. We can take like a minute mental break because we're moving on to the big question of how to find the optimal parameters, okay? Yeah, and I think I will open a new board, right? We don't want it on the same board. Okay, so we are looking at how to find. So what is the first, let's say, intuitive thing you would have thought of if you had to find the optimal parameters and you have a computer? I think most people would say, just brute force it. Look at like all the values, let's say, not to extreme values, but let's say every value between minus 100 to 100 with jumps and see which one gives you the optimal value. And that's not a bad idea. The problem is once we have a lot of parameters, let's say 10 parameters, so we need to find all the combinations of all different parameters which give you the best value, and that is just too many values to search for. So what we were trying to do is we're trying to find a trick which will help us search for the right parameters or help us in our searching method and hone in on the good parameters instead of just trying all the possible combinations of parameters, okay? So the trick we're going to learn, and this is the number one trick. There are other tricks, but this is the number one, and we're going to be using it for the rest of the course, is called gradient descent. And this is how it works. We assume, let's see, what photos do I have? I don't have a big photo. Okay, so we assume we have a loss function, right? So this is our loss value, given the data and the parameters. So for now, let's find only one parameter. We're going to call it B0. No, that'll be confusing. Let's call it B. And our data X. Let's call it small b because it's only one value. Okay. Oh, we should call it W for weight because then we don't say it's necessarily a coefficient. Something that, okay, it could be any parameter, okay? So our loss function is for different values of W. So let's say W goes from minus 100 to 100. For different values of W, what is our loss? Like we use that W in the parameter and we calculate, right? And we use the loss function. Let's say it's a mean squared error or whatever, we can use it. And you have a, so let's say the function looks something, let's do it in red. It looks something like this. That's not red. Okay. So what is our best W? That should be very easy. This one. Why? Because it gives us the lowest loss, the minimum loss, the best W, right? The problem is we don't know ahead of time which W will give us the lowest loss, right? Okay, so we have to kind of find. So the trick in gradient descent goes like this. We pick a random W. Let's say we pick this one. Let's say we pick W equals, what is this? Minus 50. Okay. And then we see what the loss is at this point, and we see, it's not that good, whatever. We don't care. We know we just picked it randomly. We know it's not the optimal one. But what we do is we calculate the derivative or the slope at this point. And we see that the derivative is negative. Now, a negative derivative for a function simply means that if you increase the W, you will get lower loss. And if you decrease the W, you will get higher loss. So what should we pick? Minus W equals minus 49 or W equals minus 51? Minus 49. Why?
Oh, yeah.
Right, it's a minus. It's not. I should have picked a more simple example. Okay, so then we tweak W by the sign of the slope, and we also tweak it by times some multiples times some value, which we call the learning rate, which is how big of a jump. So here I gave jumps of size 1, but you can also give jumps of size 2 or 10 or whatever. And then we pick the new W, and then the new W will be here, let's say. And then we calculate the slope again. And then we know which direction to jump. And let's say we pick the new W, and then the W will be here. And then we calculate the slope again, and we know which direction to jump, right? Cool. How do we calculate the slope of the loss function at a point? Derivative. We just take the derivative. It's so simple, right? We have the loss function in math, and we just derive it, right? And if we don't remember how to derive functions, we can go online. There's a derivative calculator, put the function, and it shows us the steps. That's what I do. I never remember the complicated functions, okay? Cool. If we have, and then we do it iteratively, let's say we do it 1,000 times, 1,000,000 times, whatever, until we find some W, which we hope is optimal, okay? I want to say this is an example where we tweak it only for one parameter for W. But let's say we have 2 parameters or 10 parameters. So what do? We find not only the derivative per W, but we find, so I'm going to say, if we have, let's say we have 3 parameters, 3 W's, okay? So we're, instead of finding the derivative, we're going to, the loss for one of them, we're going to find the loss or the derivative for W1. How am I going to write this? I had this written down somewhere. So what it is, we're finding the derivative or the loss or the slope in the direction of W1, in the direction of W2, and in the direction of W3, which is essentially where finding the derivative of the loss function with respect to W1, and then we find the derivative with respect to W2 and with respect to W3. And then we get a vector of 3 values, which these 3 values give us a multidimensional slope where we can step multidimensional and we tweak all the 3 parameters at the same time, each one according to its own slope. Okay, so there was a question last week. Do we first tweak the intercept and then the other ones? No, we make a vector of all the slopes, one for each of the parameter, and then we update with regards to all of the slopes at the same time. Exactly, and this gradient, gradient only means the vector of all the slopes for each parameter, is the direction in which you have to go to the hyperplane. I will say something that I forgot to say. You go into the direction negative to the slope because you want to get lower, right? So we actually go negative gradient, okay? And that's what it is. And every step, we update all of our parameters, each one by their respective slope, which is equivalent to saying we update the parameters by the gradient, because the gradient is all of the slopes. Okay?
And you do this each time for the derivatives in terms of each one.
Yes, so you have to derive the loss function in terms of each one of your parameters. Yeah, to get the gradient. So if you have a lot of parameters, you gotta do a lot of derivation. No, but usually what happens is the derivative is similar to for each one. You'll see how it works. Okay. Yes.
Sorry.
Can you repeat one more time? When the slope is negative, it means loss is high. We increase or we decrease the width.
No, when the slope, okay, so the slope doesn't mean if the loss is high or low. It just means if we increase it, does it get higher or does it get lower? So negative slope means we increase, the loss gets better, the loss gets lower. So that's what we want. And positive slope means we decrease it. Okay, and that's why I put the negative sign in front of the gradient, because we want to go against the slope. Okay, is that understood? Yeah.
So is there any, maybe this is too far, but is there any way to avoid local minimum?
Right, so that's exactly the next thing I was going to talk about. Excellent. Okay, so this is the complicated function that is the update rule, sometimes called. And oh, by the way, I should say that the loss function is calculated over all the data. So we do the loss for data point 1 plus the loss for data point 2 plus the loss for data point 3, and then we do the average loss over the whole data, right? It makes sense because we want to see the loss over all of our data points and then update. Okay, so this is what this very confusing function says. It says our new parameters, which is our new vector of weights, will be our old parameters minus, because we're going against the direction of the slope, the learning rate, which is the jump size, times the average of the loss, the derivative of the loss in regards to each one of the parameters. So this is a way to say derive the loss function for each one of the parameters. Okay, so this is the gradient. Okay, I will say that I will write that this is the learning rate. This is important.
Learning rate and then the average?
The average loss. So the gradient in regards to the average loss per parameter. So
Per data.
So this is no, okay. So the average per data point. So the average across all the data points, I should say, per different parameter. So for every parameter, you do the average loss over all the points, the average loss over all the points, which that's what the gradient gives you. The gradient, if you do your loss function, which is your loss over all of the points, right? So you do the loss for the 1 and loss for 2 and loss for 3 and loss for 4, right? And then you do the gradient. The gradient gives you for every parameter which way to step into. Okay. Yeah, so this is not stochastic, this is gradient descent. The difference, since you mentioned it, is that stochastic gradient descent, we don't go over all the data points because that's a lot of time. We go over one data point each time and we update. And batch is in the middle. We go over like 10 data points and we update 10 data points and we update. Okay? Mini batch, yeah. I call it batch, yeah. Yes.
So when you're initializing theta or b randomly here, it has nothing to do with what data points we're going over. You will still go over all of them, but you start with a random theta and you're assigning the random theta to the parameters and you move through all of them. And then as you move forward, you keep updating theta based on, you keep going through one data point after the other in normal.
So in the gradient descent, no, so you go through all of them, then you update your theta, and then you go through all of them again, and then you update your theta, and then you go through all of them again, and you update your theta.
It's after you've gone through.
Exactly, exactly. Okay, and that's gradient descent. Okay, so now.
I'm sorry, the
Yes.
M here is the number of examples, right?
M is the number of data points you have, yes.
Okay.
Okay, so what I was gonna say, okay, so we're gonna say something about this. We're gonna go to stochastic and mini batch, and then we're gonna go back to the local minimum. Remind me, okay? What's the problem with gradient descent? It is slow. That's the only problem. Why? Because you go through the entire data, all of the data. Every iteration, and a lot of times you guys probably know this, that computers can do 1 million of iterations. You just write 2 million iterations and you go, have your coffee, and they keep doing it. But it's slow, right? So what people did is they decided to say, oh, we don't need gradient descent. We do stochastic gradient descent. What does that mean? It means every time we randomly pick a data point from the data, and then we update based on that one. Okay, so stochastic JD, stochastic means random. It means instead of going through, instead of going down the loss function, the actual loss function over all the data points, we go down through the loss function for a particular data point every time randomly, and we hope that at the end it converges to the same optimal parameter, right? And then what happens is that you need more iterations, but it's much faster. Because every iteration, you're only going through one point. Okay? Is this clear? The logic is clear, right?
It's one single data point that's enough for us to update everything.
Yeah, and stochastic gradient descent. And then I have a picture, which I want to show you guys, which is this picture. Oh, and then I can also show you the formula. This is the formula for stochastic gradient descent, which you see you don't do an average over all the points. It's the same formula, but you don't do an average. I'm just gonna paste it. It's the same formula as before, but you don't do an average over all the points. You just pick a random point, okay? That's
So,
what yes.
sorry, do you still go over all the examples, but just like by one by one? Is that correct?
Well, it could be, but it could be also that you're just picking randomly and you don't see all the examples. It depends how many iterations you're willing to do.
And how do you decide that?
So you just pick, it's the same question as how do you decide the learning rate, which is also a good question. You try and pick and you see if it converges or not. So you give it, let's say 1,000 iterations or 2,000 iterations at the beginning and see if it improves. And then you tweak it and you see. But I will give you the solution. The solution is that you don't do not gradient descent and not stochastic gradient descent, but you do something in the middle, which is the batch gradient descent. Okay, but then you have to decide on the size of the batch.
Okay.
So your question does still stand. Okay, so this is an example. So this is the loss function viewed from above for 2 parameters. So the x-axis is one parameter, the y-axis is a different parameter, and we view it from above. So blue is low and red is high. We started with a random W, and then every time we go through the gradient, so we update based on tweaking W1 and W2. In gradient descent, we would tweak this, and then this, and then this, and then this, and then this. At every point, you find the actual slope towards the minima that is in the actual loss function, because it's the loss function for all the data points, right? And then you get here. Stochastic gradient descent, every time the loss function changes a little bit because of the data point, right? So you kind of jump here, then here, then here, then here, then here. A lot more jumps, but at the end, you reach pretty closely. Is this picture understood? I think it's a good way to visualize the difference between the two. Yeah, okay. I'm glad.
Double checking.
Yes.
With stochastic, you still pick a different data point each iteration.
Yes, each iteration. No, if you use the same one, you're gonna overfit for that data point, and that's not good. Very good question. Okay, and then the solution is, of course, you do mini batch or batch. I just call it batch. Batch GD, which is you pick a size, let's say size 10. Usually they go by multiples of 2 because computers like multiples of 2. So people sometimes pick size of 32 or size, 16 or whatever, but you can also pick different sizes. It also very much depends on how good your computer is, right? We know this. And then pick a size and you iterate. And every time you randomly pick a size and you iterate and you learn, okay? Cool. And we know that it is good because it's between slow and fast, right? It's in the middle, but it's also less jumpy around. It's more stable. Okay. I feel like this is very clear. I feel like you guys got this. Yes.
In gradient descent, don't the steps have to be smaller at each time?
Oh, so that's a good question. So what you're saying is gradient descent with adaptive learning rate. So usually what I just said right here is you have a learning rate. And the learning rate is multiplied by the slope, by the gradient every time, and it's the same learning rate. So every time you take a different step. But today, oh, because you say the slopes are, but no, not necessarily. It could be a function that looks like this, and then the steps get larger. It could be different ways. But today, I thought what you said, there are people who do the learning rate changes. In the beginning, you take big steps. So you say the first 1,000 iterations take big steps. The next 1,000 iterations take smaller steps, and then smaller steps. And then you kind of hone in on the point better. So that's called adaptive learning. Yeah, it's a cool thing to do. It's very easy to implement. You just add a line that changes the learning rate based on which iteration you are. Okay?
I'm sorry, I didn't get what do you mean by pick a size? Pick a size of what?
Didn't get by what I meant by what?
Pick a size, like size of what?
Oh, size of how many data points are we gonna calculate the loss derivative in regards to, right? And then update based on them. So when you look in this formula, you pick the M, which is your size of how many data points you see the loss for. Okay, so pick a size of data points to update every time. To update your weight spine. Okay. We got time, right? What? The average towards the data points that you picked. Yes, you use the average of the data points you picked. That's your will be your loss. Okay.
And well, the size is random. The window you're picking is random, but also the position that you start in the window at is also random for each iteration.
Yeah, although it's also common to just divide the data into batches and then just pick a random batch every time. It's also common to do that. I don't think it really matters how much you randomize that your data. Okay. Excellent. What else did I want to say? Oh, I want to talk about what's called the minimum minimum and maximum. No, the global and local minimum. Okay, so who can tell me the difference between a global minimum and a local minimum? Yes. Excellent. So they both have derivatives of 0, and every time you're next to them, the slope is going to point you towards them, right? Okay, so the first thing, where do we want to get on the loss function? Global, because that's the optimal parameters, like by definition, the most optimal parameters. But if we use gradient descent, it will point us to the nearest minimum, or the minimum that is step sizes away, right? So it could point us to the local minimum, right? So that problem has no explicit solution. You can, because the reason is, if you don't know the function beforehand, you don't know where your global minimum is. And if you don't know where it is, so you don't know if what you're stuck at is a local minimum or a global minimum. Okay? I think it's a good metaphor for life to sometimes see if you're in a global minimum or local minimum. Sometimes you have to make your loss be a little bit worse in order to find better place to be, a better minimum to be after. So the classic way to escape local minima is to use step sizes, which will allow you to escape local minima. So this is what this illustration, the second illustration that I put is trying to illustrate, is this. If we started over here and we take small step sizes, and in black, we're going to get stuck at a local minimum. Or medium step sizes. If we take large enough step sizes, we can make it to the global minimum. Okay? Step size is the learning rate. Exactly. Yes. But obviously, it's not so simple, because if we use too big of step sizes, we might accidentally kick ourselves out of the global minima. So we need to use a small learning rate, right? And this question of balance between how to pick the right learning rate so that we don't find a local minimum, but we kind of explore the area well around our loss function, the area, the parameter area, right? All the possible combinations of parameters which are good, but we do make it to a local minimum. It's just, it's such an important question, and there is no explicit answer. There are only tips and tricks of people who do it for a while. So people say, try it with a big one and with a large one and with a small one and see how your performances are, or stuff like that. Okay, or try it with an adaptive learning rate, which means you change it with the iterations. But honestly, if you can figure out good tips and techniques to get your model to converge better, you're going to make a lot of money. Like that's basically it. Yeah.
That doesn't mean about gradient descent also have this problem a little bit, because like the loss function is always jumping nearby the real minimum, but this never like stopping.
Yeah, so that's a good point, and that's one of the early proposed solutions was to add a little bit of randomness to your update. Once in a while, add a little bit of randomness, because that will kind of give you jumps around, and that will make you jump. And that solution, it used to be called, I forgot what it used to be called, but the logic behind it is that that's how nature does it. So nature has random mutations from time to time. It used to be called something with mutations. Nature has random mutations from time to time to kind of kick you out of a local minimum if you're in a local minimum, and maybe get you to find a new niche. So he said, oh, we're also, every time we're going to put a random mutation in, and we're going to make, our loss function is not going to improve, most likely, because if we randomly change the parameters a little bit, it's not going to be in a direction which improves our loss function, but it might help us get away from local minima and stuff. I heard that today it's less popular to do that random thing, and it's more popular to do tricks with the learning rate, adapted, but it could work. So I don't know. Also, I'm not sure. It could be that I don't know what's going on in like Google and Amazon. Maybe they know. Maybe they do the random stuff. Yes. Yeah, I wish.
When you say
Yeah, to update the parameter a little bit randomly, not exactly in the direction of the gradient. A little bit randomly, kick it up from time to time. Yes.
Doesn't the solution with bigger steps assume that the local minimum has less width than the global minimum?
Yes, it does. Yeah, I'm not sure why either. The point was to show you that bigger steps can kick you out of local minima. That was the point, to show you. But it can also kick you out of the local global min. There are also problems which are what's okay, I will go into it. There are also problems when you're optimizing over more than one parameter, so it's not just 1D, you can have saddle points. So saddle points are points which are the minima for one parameter and the maxima for a different parameter. So they look like a saddle, and their derivative is also 0, so you don't know which way to advance. But it's not even a local minimum, it's a saddle point. It's worse than a local minimum. So also adding randomness also can help kick you out of the saddle points, or make bigger learning rates can kind of make sure you don't jump to those saddle points. Okay. Excellent. So now what I want to do is to show, because we said we want a little bit review of code, is to do a gradient descent example with code, which will help you a little bit with code with Google Colab. Is that okay with everyone? I don't need you guys to code. I wrote the code already, but you can code whatever. You can do whatever you want. All right, and then that's not an alarm, is it? No. Okay. Okay, so Google Colab. So we all know how to use Google Colab, right? I hope by now. So the first thing is I'm importing NumPy and Pandas. Yes. How do I zoom in? Control plus, maybe? Is this good?
Is this in any of the folders?
No, I'll put it in the folder today. Okay.
Sorry,
Yes.
we still see
Oh, the
the
screen sharing is the wrong one. Yes, I know. Good call. Okay, can you see now, Zoom people?
Yeah, thank you.
Okay, so we imported NumPy as NP and pandas as PD. And now I'm going to explain the problem that I have. I have data, which is 60 values, or I don't know, maybe 200 values. I don't remember. A lot of values. And I want to find their average. Okay, so the data is saved as a CSV file. Okay, cool. So how do we read a CSV file from Google Colab? I open the files, the files folder. I upload my file there. And now Google Colab can reach it, can read that file. It's like in its path. Be careful, because after 12 hours of not running or whatever, your Google Colab closes and all the files that you have here are deleted. So make sure you download them at the end if you need them. In this case, we won't need it. So I'm going to use the pandas function read CSV to read the CSV value file. And then the values are just the data. Okay. Like just you'll take it. And then the true mean is the actual mean of the values. But let's say we don't know it, right? Let's say we want to use gradient descent to solve it. Okay. So I can look in my variables and I see I should have 3 variables. The data, which is a pandas data frame, which has the value and the list of all the values. The true mean, I'm not looking at it because that's cheating. And the values are the NumPy array with all the values. So we can use for later, okay? Cool. Now we're gonna initialize the mean estimate. So this is the parameter that we're trying to initialize. I initialized to 0, but we should have initialized it to be random, right? The reason I initialized to 0 because I want to make sure it starts far away enough from the real mean so we can see it learning. But it could have been random. It should have been random, right? And if we have more than one parameter, we initialize all of them to be random. We define the hyperparameters for gradient descent. So I chose the learning rate 0.1 and the number of iterations 10,000. Could have done something else. Doesn't matter. Could try and see what's going on. Okay. All right, cool. Now this is the tricksy part. No, it's not tricksy at all. We go for I in range number of iterations. For every iteration, 10,000 times. We're gonna use. Oh, I forgot to ask. How am I gonna find the mean? What is my loss function? Mean squared error, right? Because remember, there's the proof that we didn't touch today that if you optimize for the minimum mean squared error, you're also finding the mean of the distribution, right? It's the same thing as approximating. So we're going to calculate the mean square error, which will be the sum of the mean estimate minus the true mean. No, that's not what I wanted. Squared divided by length. Wait, what? I know what I did here. Okay. I did it differently than what I should have done. I should have done I didn't minimize the mean squared error. No, instead all I did is to minimize the distance between our estimate and the true mean, because I used the true mean. Right, okay. Right, because that was okay. So just what happened, my first thing was just to do it quickly to show you how it will converge to the number, to the true mean. And then I was like, no, let's show you the mean squared error. And I guess I didn't save or I didn't change it. Okay, so we're not going to go into it too much. We are going to do the gradient is just the derivative of the loss. Okay, and then the update rule, the mean estimate is the mean estimate before minus our learning rate times our gradient. Okay, and then this is a code that says if I is exactly divisible by 1,000. So if the remainder, if you divide by 1,000 is 0, then print a line that says this is the iteration. So this just shows that every 1,000 iterations, it will print a line instead of printing it every iteration. Okay, this is useful code to see that it runs. And then I'm going to click it. No, your gradient will be a vector of size 2. No, because you can't have 2 parameters for the mean estimates because the mean estimate is my parameter. here you will have two parameters, and each one will be updated by the one with the gradient, okay? And then you can see, oh, it ran very quickly. I'm surprised. So this is the first iteration. The mean was 0. And then this is my mean squared error. It's kind of big. And then it improves and improves and improves and improves and improves and improves and improves until it got to 5.19 with a mean squared error of 0.000. Probably has some error from the true mean. Okay. It's not the best example because I'm not supposed to know the true mean. I was supposed to minimize the predicted y. Doesn't matter. Okay. And then I can just print what was the actual true mean, which is 5.94, and our mean estimate is 5.92. Okay. Cool. So you guys will have to write a similar code, I think, for homework for linear regression with two parameters, right? The intercept and the slope. And I will advise you, look up Google, use Google. It's your friend. It can help you. People wrote similar codes before, can solve syntax stuff. It's okay. But make sure you understand what each line does. Okay? Excellent. By the way, this was this was meant to be stochastic gradient descent. I was supposed to use the whole thing, but instead of use but I didn't. I used just a true mean, which is like a different. Okay?
Sorry, did we have
Yes.
homework from you, or it's you mean the one from the
Same
professor?
one with us not. Same one. It's the five questions, I think. Yeah. No, we gave it. I think no. That's awful.
Yesterday.
Okay. The last thing, I feel like we're kind of good on also, but I forgot to say that I also put in the folder Python help or whatever. But actually I wouldn't use the slides that I put in, but I'd go to the first slide and the links and click on the links because there's so much better help online. People like wrote it. The last thing I want to do is to go back to the linear regression. And tell you a secret. After we learned about gradient descent, which is a way to find parameters, which will work for linear regressions, generalized linear regressions, other models which we don't have yet, right? It's just a good way, optimization way. You find a loss function and you have parameters. I will tell you that for linear regressions, specifically, not generalized linear regression, there is a simpler solution to find the optimal parameters. Okay? And now we're going to go over that simple solution. It's called the analytical solution. Analytical solution means that you plug in a formula and you immediately get the exact value for the optimal parameters instead of trying to do something iteratively or approximately or whatever. And it's very rare that we have it. So only linear regressions have it as far as I know. SVMs also have it. We'll get to it later. But most of the stuff, we don't have it and we have to use approximations. Okay? So I'm going to do it, and we can do it in 10 minutes. Rare case, linear regressions have analytical solution. So we're going to do the case of the linear regression where you only have one feature. So the simple linear regression. And then it generalizes to cases where you have more than one, the multiple linear regression, very easily. Okay, I'm just going to show you. That's not one. Okay, is it? Okay. So I should just copy the same picture that we used last time. Zoom people are seeing the board, right?
Yes.
Okay, so let's say this is X and this is Y. Just a second. Yes. So there is a measure between X and Y, which is, we know it from statistics, which is called the correlation between X and Y. Do you remember that measure, correlation? So what can you tell me about correlations? Pearson correlation. Yeah, I'm talking specifically about the Pearson's correlation. Pearson's R, yes. Excellent. So the first thing we know is that it is bound between -1 and 1. What's the interpretation of that? Right? Okay, excellent. What does it mean to be a positive correlation, or what does it mean to be a negative correlation?
With each occurrence of X, if we will observe corresponding occurrence of Y, but we don't know what the next one is.
So positive and negative do give you the direction. So that's the trick. So a positive correlation means that the higher X we have, the increase in X corresponds to an increase in Y. So
Yeah.
let's say age and wealth are correlated. The older you are, the more wealth you have. Oh, yes. There's correlation, doesn't talk about causality at all, and doesn't say which one is that you're independent and which one is your dependent variable. It's just a measure of what they are. And negative correlation means that the higher X is, the less, the lower Y will be, and vice versa. Okay. So it's bound between -1, 1, and positive means I'll do increase X means increase Y, and negative increase X is decrease Y, or decrease X is increase Y. Okay. We know this, we don't need to write this, right? If you want to fit a linear regression, oh, and do we know how to calculate the correlation? You guys don't remember the formula? It's okay. How do you calculate correlation if you need to? Go to Excel, right? You pick the two lines, you do the correlation, right? Or you go to MATLAB or Python and you do correlation, and you get that value. There is the formula. The formula is the correlation is the average of X minus the mean of X. No, what is the average of? Okay, I'm going to look it up just a second. I don't want to make sure, but it's something divided by something. We'll get to it very soon. So let's say we have the correlation. So the correlation is the covariance divided by the standard deviations, and the covariance is the normalized X score times the normalized Y score for each XY point. But I'm just gonna print out the formula here in a second. So, and we want to fit the formula Y tag equals B0 plus B1 times X. So this is crazy, you might not believe me. We can immediately get B1 as a solution. It is R times the standard deviation of Y divided by the standard deviation of X. Okay, so that's immediately the optimal slope parameter. Once we have the correlation, that is we also get the slope parameter. We just have to multiply it by the standard deviation, by the ratio of the standard deviations. And that is why in every academic paper that I know, when you find the correlation, you plot a linear graph and there's a line going in between. Right? You guys see these plots. Okay, so that's why, because the correlation and the linear regression are it's the same thing, it's just multiplied by the standard deviation. Like it's the same thing, it's measuring the same thing. Okay, cool. And then B0, how do we find B0? Just so I'm not messing this up. Is the mean of Y minus B, the mean of X. So B0 equals Y hat minus B1 times X hat. And I'm just going to put the hats quickly. Hat means mean, right? And that is a very quick and nice analytical solution. And then what I'm going to tell you guys is for the homework. I know you're supposed to find the regression using gradient descent. But if you want to check how good your gradient descent is, find it here, the analytical solution, and see how close you got. Okay, so that's a good tip. Okay. Wait, I want to find the correlation formula. So you guys have it. Yeah, this is the one. Please work. Ah. Good call. But you guys are grad students, you should know how to calculate a correlation without going through the formula. No, just you guys have had to have some seminar where you had to calculate a correlation with more than 10 numbers, and then you see that the formula is crazy. You just use Excel or something, right? Have to be. Okay, cool. And then I'm just going to generalize what happens if we have more than B1, one B1. What happens if we have a lot? So the formula is the parameter. Oh, we're going to finish on time. Good job. So it's a multiple regression. Multiple regression just means we have more than one feature. And then the parameter vector, that here they wrote the theta vector, is equal to the X matrix transpose times X, the inverse of that matrix times the X matrix transpose times Y. Now this is a lot of linear algebra, and I don't expect any of you to know how to calculate these things by hand, especially when you have a lot of data points, but this will give you the solution, okay? And then here is something that is useful to know. When you do a linear regression, I think almost most packages online, at least that I know of, do solve it analytically. And then when you do a generalized linear regression, they can't solve it analytically, so they use some form of gradient descent. Why is this useful? Because you will see that the linear regression runs very quickly on your computer because there's an analytical solution, and the GLMs sometimes take longer to run. So it could take minutes or even longer. So don't be afraid. Don't be like, oh, why is this? What am I doing wrong? This is why, okay? Also, for every function that I know, you can ask it, the linear regression, to also use gradient descent or a different method if you want, if you don't trust the analytical solution. Okay, but you should trust it. Cool, we good? All right, is there questions about this? So just to reiterate what we did in this lecture, we did I'm gonna open the picture. We added 2 more twists to the linear regressions, and we're done with linear regressions. We said that we can assume Y comes from a problem. This is very small. Oh, and the Zoom people don't even see it. Okay. We added 2 more twists to the linear regression. We said that we can add a probability distribution, which will let us maximize the likelihood, which is something that we like. It has an interpretation, and that's a new family of loss functions that we can have. And we can also make generalized linear regressions, which is an extension, a nonlinear extension of linear regressions. And then we talked about a few of them. And then we talked about gradient descent, which you guys got intuitively very, very quickly, probably because you learned it already. Stochastic gradient descent, batch gradient descent, update rule, learning rate, what is the gradient? And then we said that specifically for linear regressions, there's the analytical solution, which can use the correlation. Okay. Cool. Any questions? Any questions about this? Any questions about coding? Any questions about the homework? Do you want to go through the proof that, I'm done, we can go, but if anyone wants to go through the proof that the maximum likelihood estimate for the normal distribution is equal to the minimized mean square error? No, guys.
Yeah, it would be great.
Yeah, it will be good. Okay, so we can go through it. I also put it on the drive. Okay, whoever wants to go can go. Whoever wants to ask me questions can ask me questions. Whoever wants to stay and go through that proof, we'll go through that proof. The proof that the parameters which give you the max likelihood estimation for the normal distribution are the same parameters which will give you the minimum mean squared error.
Okay.
Right? Because remember we said it's a specific case. It's cool that it happens. In science, a lot of times you're going to hear I fit a linear regression using the minimum mean squared error. And what the reason for that is because you use the you're looking for the maximum likelihood, because in science it's very common to look for maximum likelihood. That's what statistics is all about, looking for estimators which maximize likelihood.
Is this recorded because we need to have lunch right?
Oh, this, yeah, we're recording this, right? Yeah. Yeah.
Thank you.
Okay. You can also feel free to eat lunch here if you have your lunch. Oh, you can do whatever you want. Okay.
I'm so sorry. I
Yes.
still don't understand what you mean by maximum likelihood error.
Oh, okay. So I'll explain it again in, wait, I want to show. Okay, I'll say it in words, but worst case scenario, if you don't understand, we'll write it down. The maximum likelihood estimator means that this probability distribution needs some parameters, right? So for example, the binomial distribution needs the P parameter, which is the probability of something happening, right?
Yes.
Yes. And then we want to find the parameter which will make the probability of us seeing the data that we saw from this parameter the highest. So in my example, I gave the gold coin example, which landed 7 times heads.
Mm-hmm.
So if we assume that the chance of heads is very, very, very small, 0.001, how likely is it that we saw 7 heads? Very low. Because if the likelihood for heads is very, very small, seeing 7 times heads is it's very unlikely. But if the likelihood of seeing heads is some value, let's say 0.7, then the likelihood of seeing 7 heads in that for that coin is higher than if the probability for heads was low. Right?
Okay.
Is that intuitive? So what
okay.
is the parameter which will give us the maximum likelihood. It's most likely to see that data from that, if that's the real parameter, the data that we saw. Okay?
Okay. Yes.
Yeah. And it's a fancy way to say something that's very intuitive, is that we look for the parameter which best fits the data. Okay. So
okay. Thank you.
Going through the proof. Logarithm rules, we all know that the log of e to, this is the natural logarithm, log of e to the power of something equals that something, right? We know this. Log of 2 values multiplied, P1 times P2 equals the sum of their logs, log of P1 plus log of P2. And log is monotonic, so the values that maximize f of x, some function, will also maximize log f of x. Okay, so you can take your loss function and you can multiply it by any monotonic function, and it will still, the same parameters will maximize it. Okay, makes sense. Maximizing the likelihood means to find the parameter mu for the normal distribution. It means to find the parameter mu, which is some parameter from a function of all our betas or parameters or whatever, or feature or weights times our features, that will maximize the probability of us seeing y, observing y, which we observed, given that mu. Okay, so this is the maximum of the likelihood. This is the likelihood of seeing y given the parameter, and we want the maximum. Okay, so this is a different way to say we want to find the parameter mu, which will give us the maximum of the probability of seeing y1 given mu1 times the probability of seeing y2 given mu2 for all the data points, all the y's that we observed, because the likelihood of seeing all the points is the likelihood of seeing this point times the likelihood of seeing this point times the likelihood of seeing this point, and so on. Yes.
Is the mu one of the technos?
No, the mu is what happens when you multiply all the thetas by all the x's. It's your estimate. It's like your line. It's like your predicted line. Okay. Excellent. So we can assume that each point is independent. So the probability of seeing all the points is the is the probability of seeing each point multiplied by the other, right? It's probability of seeing the first observation times seeing the second observation times seeing the third. And then we can use the logarithm rules, which will do, it's a logarithm of seeing the probability of the first point plus the logarithm of seeing the second point plus the logarithm for all the points, okay? It's the same thing. And then essentially what we're trying to find is the maximum, is the mu, which will give us the maximum sum of all the log of its probabilities. So this is a different way to say that we're trying to find the maximum log likelihood. Instead of the likelihood, the log likelihood. And this will just help us because instead of writing multiplications, we're doing sums, which is just easier to write. Yes?
I think I'm confused with the letters. So mu is the prediction and y
is the actual observation, is the outcome, is the actual outcome. Yeah.
The outcome.
So let's say I want to measure your score based on your hippocampus size.
Oh, yeah.
So y is your score,
Mhm.
and mu is your predicted score based on your hippocampus size. Okay, excellent. So essentially, we want to find the mu, which will maximize the sum of all the log of the probabilities, of all the logs of the probabilities, which is the same way of saying which will maximize the product, the multiplication of all the probabilities. So how do we calculate the probability of y given mu in a normal distribution? We use the normal distribution PDF formula. So the normal distribution formula, it's very ugly. That's how it looks like. So I just substituted it in, and this is it's some constant times e to the power of our y minus the mu divided by another constant. These are not exactly constant because they have standard deviations in them, but here we're only optimizing for the parameter mu, which is the mean of the normal distribution. We're not optimizing for the standard deviation. Okay. And then we can break it down just by logarithm and addition rules that we want to find the mu, which will maximize this over all the points, is to find the mu, which will maximize this and maximize this. Okay, this is just by the log rule that multiplication becomes addition, and by addition rule, you can add these separately and then this part of the formula and this part. Okay, and we see that the first part of the formula is a constant. It doesn't depend on mu at all or on the y's, right? So we can discard it because if you want to maximize some loss function, it doesn't matter if you add a constant or take away a constant from that loss function, the same parameters will still maximize it. So we're trying to maximize the log of e to the power of, here we do have our y's and our mu, so we can't discard this. Obviously, we want to find the mu, which will make this the highest. Using the logarithm rule, log of e to the power of something is just that something. Okay. And we can take the negative sign and put it outside the sum because that's addition rules. So we want to find the maximum of the sum, the maximum of negative the sum of all the y's minus our mu's squared divided by 2 sigma squared or 2 variance. Okay. And then we know that maximizing a negative is the same as minimizing the positive. Okay, so this is what we get. We also know that 1 divided by 2 sigma squared is a constant here because we're not optimizing for sigma, so we can also discard it. And we get that we are trying to minimize the yi, the sum of yi minus mu I squared for all our data points. And this came from the normal distribution PDF up here, this thing. This is where it came from, okay? And there's an intuition behind it. The intuition is maximizing the likelihood for the parameter means finding the parameter mu for the normal distribution, which will minimize the square distance of each observation from it. So there's kind of intuition here that the average of the distribution will minimize the squared error from that average. I think it's intuitive a little bit, but we got to it strictly by math. Now we show finding the minimum MSE means to find a y hat, a predicted, which is also a function of the theta or the betas times x that will minimize the MSE formula. And obviously 1 over n is a constant, so we can discard it. And then we have to find the minimum sum yi, the actual observation minus our predicted observation squared. And now it's clear to see that these are the same formula when the predicted line is the minimum, is the mu, is the mean of the distribution, of the normal distribution. So what I wrote is finding the maximum likelihood estimate parameter mu, or parameters, is equivalent to finding the minimum MSE parameters when our mu is equal our predicted, our y hat. Okay? Excellent. I'm going to stop sharing now. And we can stop the recording, I think.